Hello, my name is Paul Geyer, and I'm here to chat with you today about the distribution of stresses in soils. This is what I will be talking about today. Stress conditions at a point, stresses beneath structures and embankments and shallow pipes and conduits, deep underground structures, very limited comments on numerical stress analysis, and then most importantly, a list of very important reference publications. All of the information that you need to address stresses at points in soils is not contained in this publication. You're going to have to use this publication in concert with the appropriate references that are listed in section 7. So again, it is important for you to understand this right at the beginning. Thanks a lot. And by way of introduction, this is just a little bit about me and what I've been doing for the last few decades. This discussion covers the analysis of stress conditions at a point, stresses beneath structures and embankments, and empirical methods for estimating loads on buried pipes, conduits, shafts, and tunnels. Stresses in earth masses are analyzed using two basic and different assumptions. One assumes elastic conditions and the other assumes full mobilization of shear strength, that is, plastic equilibrium. Elastic solutions apply to problems for which shear failure is unlikely. If the safety factor against shear failure exceeds about 3, stresses are roughly equal to values computed with elastic theory. Plastic equilibrium applies in problems of foundations or slope stability and wall pressures where shear strength may be completely mobilized. If normal and shear stresses at one orientation on an element in an earth mass are known, stresses at all other orientations may be determined from Mohr's circle. The use of Mohr's circle for plastic equilibrium is illustrated by analysis of triaxial shear test results. The normal stress at any orientation in a saturated soil mass equals the sum of two elements: pore water pressure carried by fluid in soil spaces and effective stress carried by the grained skeleton of the soil. The total stress at any point is produced by the overburden pressure plus any applied loads. Pore water pressure may consist of hydrostatic pressure, capillary pressure, seepage, or pressure resulting from applied loads to soils which drain slowly. Effective stress equals the total stress minus the pore water pressure, or the total force in the soil grains divided by the gross cross-sectional area over which the force acts. Division of weight of overlying soil and water into effective stress and pore water pressure depends on the position of the groundwater table or the flow field induced by seepage. For static water condition, effective stresses at any point below the groundwater level may be computed using the total unit weight of soil above the water level and buoyant unit weight below the water level. Pore water pressure is equal to the static head times the unit weight of water. If there is steady seepage, pore pressure is equal to the piezometric head times the unit weight of water, and the effective stress is obtained by subtracting the pore water pressure from the total stress. Division of applied load between pore pressure and effective stress is a function of the boundary conditions, the stress-strain properties, and the permeability of the stressed and surrounding soils. When drainage of pore water is inhibited, load is compensated for by increased pore water pressure. These pressures may decrease with time as pore water is drained and load is transferred to the skeleton soil, thereby increasing effective stress. Analysis of a soil system, including settlement and stability analyses, are performed either in terms of total stresses or effective stresses. The choice between the two analysis methods is governed by the properties of the surrounding soils, pore water behavior, and the method of loading. With regard to stresses beneath structures and embankments, semi-infinite elastic foundations, the assumed conditions, the following solutions assume elasticity, continuity, static equilibrium, and completely flexible loads so that the pressures on the foundation surface are equal to the applied load intensity. For loads of infinite length, or where the length is at least 5 times the width, the stress distribution can be considered plane strain, i.e. deformation occurs only in planes perpendicular to the long axis of the load. In this case, stresses depend only on direction and intensity of load and the location of points being investigated and are not affected by elastic properties. Shearing stresses between an embankment and its foundation are neglected. Below a depth of 3 times the width of a square footing or the diameter of a circular footing, the stresses can be approximated by considering the footing to be a point load. A strip load may also be treated as a line load at depths greater than 3 times the width of the strip. Computation procedures for common loading situations are as follows for vertical stresses beneath regular loads. Square and strip foundations. For more accurate computations, use standard methods. For a rectangular mat foundation, for points beneath the mat, divide the mat into 4 rectangles with their common corner above the point to be investigated. Open influence values for the individual rectangles and the sum of the values to obtain the total. For points outside the area covered by the mat, use superposition of rectangles and add or subtract appropriate values to obtain the resultant. For uniformly loaded circular areas, use standard methods. For fills of more complicated cross-section, add or subtract portions of this basic embankment load. For a symmetrical triangular fill, set dimension B equal to 0 and add the influence values for 2 right triangles. For sloping fill of finite dimension, use standard methods for stress beneath the corners of a finite sloping fill load. For vertical stresses beneath irregular loads, use standard methods for complex loads where other influence diagrams do not suffice. Proceed as follows. Draw a circle of convenient scale and the concentric circles shown within it. The scale of the circle may be selected so that when the foundation plan is drawn using a standard scale, say 1 inch equals 100 feet, it will lie within the outer circle. Plot the loaded area to scale on this target with the point to be investigated at the center. Estimate the proportion of the annular area between adjacent radii which is covered by the load. To determine a profile of vertical stresses for various depths beneath a point, the target need not be drawn. Obtain influence values for different ordinates from the influence chart. Elastic analysis is utilized to determine horizontal stresses on unyielding walls from surcharge loads and pressures on rigid buried structures. With regard to shear stresses, elastic solutions generally are not applicable when shear stresses are critical, as in stability problems. To determine if a stability analysis is required, determine the maximum shear stress from elastic formulas and compare this stress with the shear strength of the soil. For embankment loads, maximum shear stress in the foundation is exactly or approximately equal to P divided by P sub I, depending upon the shape of the load and point in question. If the maximum shear stress equals shear strength, plastic conditions prevail at some point in the foundation soil, and if the load is increased, a larger and larger portion of the foundation soil passes into plastic equilibrium. In this case, failure is possible and overall stability must be evaluated. With regard to layered or anisotropic foundations, actual foundation conditions differ from the homogeneous isotropic semi-infinite mass assumed in the Boussinesque expressions. The modulus of elasticity usually varies from layer to layer, and soil deposits frequently are more rigid in the horizontal direction than in the vertical. With regard to a Westergaard analysis, the Westergaard analysis is based on the assumption that the soil on which load is applied is reinforced by closely spaced horizontal layers which prevent horizontal displacement. The effect of the Westergaard assumption is to reduce the stresses substantially below those obtained by the Boussines equations. The Westergaard analysis is applicable to soil profiles consisting of alternate layers of soft and stiff materials, such as soft clays with frequent horizontal layers of sand having greater stiffness in the horizontal direction. With regard to layered foundations, when the foundation soil consists of a number of layers of substantial thickness having distinctly different elastic properties, the vertical and other stresses are markedly different from those obtained by using the Boussines equation. With regard to rigid surface layer over weaker underlying layer, if the surface layer is the more rigid, it acts as a distributing mat and the vertical stresses in the underlying soil layer are less than the Boussines values. With regard to a weaker surface layer over a stronger underlying layers, if the surface layer is less rigid than the underlying layer, then vertical stresses in both layers exceed the Boussines values. Use these influence diagrams to determine vertical stress distribution for settlement analysis involving a soft surface layer underlain by stiff material. If there is no distinct change in the character of subsurface strata within the critical depth, elastic solutions for layered foundations need not be considered. Critical depth is the depth below the foundation within which soil compression contributes significantly to surface settlements. For fine-grained compressible soils, the critical depth extends to that point where applied stress decreases to 10% of effective overburden pressure. In coarse-grained material, critical depth extends to that point where applied stress decreases to 20% of effective overburden pressure. A rigid foundation must settle uniformly. When such a foundation rests on a perfectly elastic material, in order for it to deform uniformly, the load must shift from the center to the edges, thus resulting in a pressure distribution which increases towards the edges. This is the case for clays. In the case of sands, the soil near the edges yields because of the lack of confinement, thus causing the load to shift towards the center. Estimates of the vertical stresses induced in a soil mass by an axially loaded pile are calculated for both friction and end-bearing piles. With regard to shallow pipes and conduits in general, pressures acting on shallow buried pipe and conduits are influenced by the relative rigidity of the pipe and surrounding soil, depth of cover, type of loading, span, maximum width of structure, method of construction, and shape of pipe. This discussion describes simple procedures for determining pressures acting on a conduit in compressible soil for use in conduit design. For detailed analysis and design procedures for conduits in backfilled trenches and beneath embankments, consult one of the following: Buried Structures by Watkins, Design and Construction of Sanitary and Storm Sewers by ASCE, Handbook of Drainage and Construction Products by Armco, Engineering Handbook Structural Design by the U.S. Department of Agriculture, Concrete Pipe Design Manual by the American Concrete Pipe Association, or the CANDE User Manual by Katona and Smith. Pipes made from precast or cast-in-place concrete or cast iron are considered rigid pipes. With regard to vertical loads, first the dead loads. Vertical soil pressure estimates for dead loads are obtained from the equation indicated, with the elements of the equation defined as indicated on this slide. For soils of unit weight other than 100 pounds per cubic foot, adjust proportionately. For example, U equals 120 PCF, multiply chart by 1.20. Live loads, vertical pressure due to surface load, P sub LL is calculated. Impact factor is included in the live load if it consists of traffic load. For example, an H20 truck loading consists of two 16,000-pound loads applied to two 10 by 20 inch areas. One of these loads is placed over the point in question, the other is 6 feet away. With regard to design of rigid conduit, to design a rigid conduit, the computed loads, dead and live, are modified to account for bedding conditions and to relate maximum allowable load to the three-edge bearing test load D. See ASTM C76, reinforced concrete culvert, storm drain, and sewer pipe for test standards for the D load. Bedding conditions for pipes and trenches may be accounted for by use of a load factor L sub F. Determine D from the following equation indicated on slide 24 with the quantities, with the components of the equation as defined on this slide. With the specified D load, the supplier is able to provide adequate pipe. The soil pressure against the sides of a pipe in an embankment significantly influences the resistance of the pipe to vertical load. The load factor for such cases considers not only pipe bedding but also pipe shape, lateral earth pressure, and the ratio of total lateral pressure to total vertical pressure. With regard to flexible steel pipe, corrugated or thin wall smooth steel pipes are sufficiently flexible to develop horizontal restraining pressures approximately equal to vertical pressures if backfill is well compacted. Vertical exterior pressure acting at the top of the pipe may range from pressures exceeding overburden pressure in highly compressible soils to much less than the overburden pressure in granular soils because of the effect of arching, in which a proportion of the overburden pressure is supported by the surrounding soil. With regard to vertical loads on shallow pipes and conduits and the dead load, for flexible pipe, the dead load pressure is simply the height of the column of soil above the conduit times the unit weight of the backfill, as indicated by the formula on this slide 26. With the live load, it is computed by Boussines equations for rigid pipes. With regard to pressure transfer coefficient, the dead load and live load pressures are modified by pressure transfer coefficient C sub P to yield apparent pressure P to be used in the design using the formula indicated on this slide 26. With regard to initial design, use the following suggested procedures. Determine the apparent ring compression stress of the pipe using the formula indicated on this slide 27 with the components of the equation as indicated on this slide. Equate the apparent ring compression stress to allowable ring compression strength to determine required cross-sectional wall area A per unit length of pipe using the equations indicated here. Select appropriate pipe size to provide the minimum cross-sectional wall area A as determined above. Check the ring deflection so that it does not exceed 5% of the nominal diameter of the pipe. Ring deflection Y is governed by the total soil pressure P sub V equal to P dead load plus P live load, diameter D, moment of inertia I, modulus of elasticity of conduit E, and soil modulus E prime. Generally, ring deflection does not govern the design. The handling factor is the maximum flexibility beyond which ring is easily damaged. Pipe design must consider limiting the handling factors to such typical values as d squared divided by EI with the limitation as indicated here. Soil placement, great care must be exercised. In soil placement, ring deflection and external soil pressures are sensitive to soil placement. If a loose soil blanket is placed around the ring and the soil is carefully compacted away from it, soil pressure is reduced considerably. For analysis and design procedures for large size flexible pipe of non-circular cross-section, refer to the appropriate technical literature. Design of culverts and conduits beneath narrow-crested embankments must consider the effect of the embankment base, spread, and settlement on the pipe. With regard to longitudinal extension, the maximum horizontal strain of a conduit beneath an embankment or earth dam occurs under the center of the fill. Maximum strain depends on the ratios B divided by H, B divided by D, and the average vertical strain in the foundation beneath the center of the fill. With regard to joint rotation in shallow pipes and conduits, besides the horizontal extension of the conduit, additional joint opening may occur at the bottom of the pipe because of settlement under the embankment load. For concrete pipe in sections under 12 feet long, compute additional joint opening due to settlement by the equation indicated on this slide 31 with the components of the equation as indicated. With regard to pipe selection, compute total settlement below embankment. From this value, compute the maximum joint opening at the pipe mid-height as indicated above. Add to this opening the spread at the top or bottom of the pipe from joint rotation computed from the equation above. Specify a pipe joint that will accommodate this movement and remain watertight. If the joint opening exceeds a safe value for precast concrete pipe, consider cast in place conduit in long sections with watertight expansion joints. Corrugated metal pipe is generally able to lengthen without rupture, but it may not be sufficiently corrosion resistant for water retention structures. With regard to long span metal culverts, the above methods are not applicable to very large flexible metal culverts, that is, those with widths in the range of 25 to 45 feet. For analysis and design procedures for these, refer to the appropriate technical literature. For deep underground openings, general factors, pressure acting on underground openings after their completion depend on the character of the surrounding materials, inward movement permitted during construction, and restraint provided by the tunnel lining. Stress analysis differs for two rock groups: sound, non-swelling rock that can sustain considerable tensile stresses, and fractured, blocky, seamy, squeezing, or swelling rock. With regard to sound rock, determine stresses surrounding tunnels or openings in intact isotropic rock such as crystalline igneous types or homogeneous sandstone and limestone by elastic analyses. For these materials, stresses in rock surrounding spheroidal cavities are lower than those for tunnels with the same cross-section. Use elastic analyses to determine the best arrangement of openings and pillars, providing supports as required at locations of stress concentrations. With regard to broken and fractured rock, pressure on tunnels in chemically or mechanically altered rock must be analyzed by approximate rules based on experience. With regard to squeezing and swelling rocks, squeezing rocks contain a considerable amount of clay. The clay fraction may be from non-swelling kaolinite group or from highly swelling morilionite group. These rocks are preloaded clays and the squeezing is due to swelling. The squeeze is intimately related to an increase in water content and a decrease in shear strength. With regard to loads on underground openings in rock, the vertical rock load application of standard methods of analysis gives the height of rock above the tunnel roof, which must be supported by the roof lining. With regard to horizontal pressures, determine the horizontal pressure on tunnel sides by applying the surcharge of this vertical rock load to an active failure wedge. Assume values of rock shear strength on the active wedge failure plane, which allow for the fractured or broken character of the rock. Evaluate the possibility of movement of an active failure plane that coincides with weak strata or bedding intersecting the tunnel wall at an angle. With regard to support pressures as determined from rock quality, as an alternative method of analysis, use empirical correlations found in the technical literature to determine required support pressures as a function of rock mass quality. The analysis incorporates rock quality designation and various joint properties of the surrounding material and is applicable for sound or fractured rock. Results may be used directly for evaluating type of roof or wall support required. With regard to openings in soft ground and the ground behavior, the method of construction of tunnels depends upon the response of the ground during and after excavations. The stand-up time depends upon the type of soil, the position of groundwater, and the size of opening. Depending upon the response during its movement period, the ground is classified as firm, raveling, running, flowing, squeezing, or swelling. In firm ground, no roof support is needed during excavation and there is no perceptible movement. In raveling ground, chunks or flakes of material begin to fall prior to installing the final ground supports. Stand-up time decreases with increasing size of excavation. With rising groundwater, raveling ground may become running ground. Sand with clay binder is one example of this type of soil. In running ground, stand-up time is 0. The roof support must be inserted prior to excavation. Removal of side supports results in inflow of material which comes to rest at its angle of repose. Dry, cohesionless soils fall into this category. Flowing ground acts as a thick liquid and it invades the opening from all directions, including the bottom. If support is not provided, flow continues until the tunnel is completely filled. Cohesionless soil below groundwater constitutes flowing ground. Squeezing ground advances gradually into the opening without any signs of rupture. For slow advancing soil, stand-up time is adequate, yet the loss of ground results in settlement of the ground surface. Soft clay is a typical example of squeezing ground. Swelling ground advances into the opening and is caused by an increase in volume due to stress release and/or moisture increase. Pressures on support members may increase substantially even after the movement is restrained. With regard to loss of ground, as the underground excavation is made, the surrounding ground starts to move toward the opening. Displacements result from stress release, soil coming into the tunnel from raveling, runs, flows, etc. The resulting loss of ground causes settlement of the ground surface. The loss of ground associated with stress reduction can be predicted reasonably well, but the ground loss due to raveling, flows, runs, etc. requires a detailed knowledge of the subsurface conditions to avoid unacceptable amounts of settlement. With regards to loads on deep underground openings, the support pressures in the underground openings are governed by the unit weight of the soil, groundwater table, soil properties, deformations during excavation, interaction between soil and the supports, shape of the opening, and the length of time that has elapsed since the installation of lining. Other factors, such as the presence of another opening adjacent to it, excavation of a large deep basement near an existing opening, load from neighboring structures, and change in groundwater conditions will also affect the design pressures on the tunnel supports. With regard to pressure on vertical shafts in deep underground openings, shafts in sand, in the excavation of a vertical cylindrical shaft, granular soils, pressures surrounding the shaft approach active values. If outward directed forces from a buried silo move the silo walls into the surrounding soil, pressures approach passive values as an upper limit. See the technical literature for active and passive pressure coefficients for a cylindrical shaft of unlimited depth in granular soils. For relatively shallow shafts, depth less than twice the diameter, rigid bracing at the top may prevent development of active conditions. In this case, horizontal pressures may be as large as at-rest pressures on a long wall with plane strain in the surrounding soil. If groundwater is encountered, use submerged unit weight of sand and add hydrostatic pressure. Pressure on walls of shafts in soft clay. For a cylindrical shaft, no support is needed from the ground surface to a depth as defined on this slide 43. To determine the approximate value of ultimate horizontal earth pressure of a shaft lining at any depth z, use the formula indicated on this slide 43 with the components of the equation as indicated here. This pressure is likely to occur after several months. Table 1 indicates loads for temporary supports in earth tunnels at depths as specified. And slide 45 is a continuation of table 1, the loads for temporary supports in earth tunnels at depths as indicated. With regard to pressure on walls of shafts in stiff clay, on shafts located in stiff, intact, or fissured swelling clays, initially the pressure on the shaft lining is very small. Over a period of time, the pressure may increase to several times the overburden pressure, that is, ultimately to the swelling pressure if shaft lining is sufficiently rigid. Local experience in that soil or field measurements can provide useful information. Stress analysis using numerical methods and computers, of course, has greatly advanced in recent years, and these are tools that are available for many simple as well as more complex loading conditions. Now to part 7 of this discussion is a list of very important references that you will have to use in addressing these types of soil stress issues. And again, to emphasize, you cannot apply the information contained in this discussion just as a freestanding piece of information. It must be applied in compliance with the technical guidance provided in these references. So keep that in mind. And flipping through the references here rather expeditiously, many of them may be known to you already. And that brings us to the conclusion of this brief discussion of stresses in soils. And again, you must use the information contained in this discussion in a concert with the appropriate technical literature, much of which is indicated in the references here. With that caveat having been repeated now for about the third time, let me again thank you very much for letting me chat with you today, and have a nice rest of the day.